Hello and welcome back. Today in Lecture 3-2, we will continue our discussion of Fourier series. The objectives of today's lecture are to describe how to use Fourier series to describe a periodic signal, to understand the process to find Fourier series coefficients, and to create the spectrum plot for a Fourier series. Recall from the prior lecture that a Fourier series is used to represent periodic signals. It is an expansion of periodic signals in terms of complex exponentials or sinusoids at harmonic frequencies of omega naught. Let x of t be periodic with fundamental period t naught and fundamental frequency omega naught. Then the Fourier series can be written as x of t is equal to the summation k equals negative infinity to infinity x of k e to the jk omega naught t. This is complex exponential form for a Fourier series. In this lecture, we will see another form as well, which we call cosine form, where the Fourier series coefficient x of k is 1 over t naught, the integral over 1 period t naught, x of t e to the negative jk omega naught t dt. The complex exponential form is used for real value or complex valued x of t. When x of t is real valued in time, then x of t equals x conjugate of t, and then we can say that it has conjugate or Hermitian symmetry, which we have proven in a prior lecture. And this implies that the magnitude has even symmetry, so the magnitude of x of k equals the magnitude of x of negative k, and the phase has odd symmetry, which means that the angle x of k is equal to negative the angle of x of negative k. Now we will show how to rearrange the Fourier series to get the cosine form when you have a real valued x of t. X of t is equal to the summation from k equals negative infinity to infinity of x of k e to the jk omega naught t, which equals the summation from k equals negative infinity to infinity of the magnitude of x of k e to the j k omega naught t plus the angle x of k. So this can be written by expanding it out as the following, the magnitude of x of negative 2 e to the j negative 2 omega naught plus the angle x of negative 2 plus the magnitude of x of negative 1 e to the j negative omega naught t plus the angle for x of negative 1 plus x, the magnitude for x of 0 plus the magnitude for x of 1 e to the j omega naught t plus the angle for x of 1 plus the magnitude for x of 2 e to the j 2 omega naught t plus the angle for x of 2. So now, since we know that x of k obeys Hermitian symmetry, I can replace my magnitudes x of negative 2 and x of negative 1 with magnitude x of 2 and magnitude x of 1. And I can replace my angle x of negative 2 with negative angle x of 2 and my angle x of negative 1 with negative x of 1. So this now becomes the magnitude of x of 2 e to the negative j 2 omega naught t plus the angle of x of 2 plus the magnitude of x of 1 e to the negative j omega naught t plus the angle for x of 1 plus the magnitude of x of 0 plus the magnitude of x of 1 e to the j omega naught t plus the angle for x of 1, and finally plus the magnitude of x of 2 e to the j 2 omega naught t plus the angle for x of 2, and both of these are plus because these would go on forever to negative and positive infinity. Using Euler's identity, I can now rewrite x of t as x of t equals x of 0 plus 2 times the magnitude of x of 1, the cosine of omega naught t plus the angle for x of 1, plus 2 times the magnitude of x of 2 times the cosine of 2 omega naught t plus the angle x of 2, plus dot, dot, dot. Or in compact form for my cosine, x of t x of t is equal to x of 0, the summation from k is equal to negative infinity to infinity, 2 times the magnitude of x of k, cosine k omega naught t plus the angle for x of k. This yields the following form for the periodic signal x of t. X of t is equal to x of 0 plus the summation from k equals 1 to infinity, 2 times the magnitude of x of k, cosine k omega naught t plus the angle x of k. Note that all physical signals are real valued. Computer-generated signals can be complex valued, though. Example 1. For the following signal, find the magnitude and the phase spectrum. So first we have x of t is equal to cosine 2 pi 3000 t plus 2 sine 2 pi 5000 t. So the fundamental frequency for that first term is omega naught 1 is equal to 2 pi 3000. And for the second term, we have omega naught 2 equals 2 pi 5000. So the fundamental period for the first term is 1 over 3000. And the fundamental period for the second term is 1 over 5000. So now we want to find the fundamental period between these two terms. So we know that T naught must equal n times T naught 1, which equals m times T naught 2. So we have n over 3000 equals m over 5000. Or we can write this as 5n equals 3m. So when m is equal to 5 and n is equal to 3, we can use this to get our fundamental period of T naught is equal to 3 over 3000, which also equals 5 over 5000. So the fundamental period for the signal x of t is 1 over 1000 seconds. So omega naught would be equal to 2 pi over T naught, which is 2 pi 1000 radians per second. So now we're going to solve for x of t. So x of t equals the summation from k equals negative infinity to infinity, x of k, e to the jk omega naught t, so that's e to the jk 2 pi 1000 t. Or we can write this as the summation from k equals negative infinity to infinity, x of k, e to the jk 2000 pi t. We can use Euler's identity to rewrite x of t as x of t is equal to 1/2 e to the j 2 pi 3000 t plus 1/2 e to the negative j 2 pi 3000 t plus 2 over 2j e to the j 2 pi 5000 t minus 2 over 2j e to the negative j 2 pi 5000t. And we see here that the Fourier series is made of 4 terms, where this one would be k is equal to 3, this one would be k is equal to negative 3, this one would be k is equal to 5, and this one would be k is equal to negative 5. So the Fourier series coefficients are x of 3 is equal to 1/2, x of negative 3 is equal to 1/2, x of 5 is equal to 1 over j, and x of negative 5 is equal to 1 over negative j. X of k is equal to 0 for all other k. To make the magnitude and phase spectrum, we need to separate our Fourier series coefficients into their magnitude and their phase. So what you'll find here is that the magnitude of x of negative 3 is equal to the magnitude of x of 3, which is equal to 1/2. And the magnitude of x of negative 5 equals the magnitude of x of 5, which equals 1. The angle for x of negative 3 equals the angle for x of 3, which equals 0. However, the angle for x of negative 5 is 1 over negative j. So 1 over negative j has an angle of 90 degrees. And the angle for x of 5 would be 1 over j, which has an angle of negative 90 degrees. So now let's take a look at the spectrum plot. So here we have the magnitude and phase spectrum for this example. The first plot is a plot of the signal x of t equals cosine 2 pi 3000t plus 2 times the sine of 2 pi 5000t. And what you should see here is that the signal actually is periodic and that it repeats every 1 millisecond. And then here we have our magnitude spectrum, where down here we do have a magnitude of 1 at negative 5 omega naught, or k equals negative 5. We have a magnitude of 1/2 at negative 3 omega naught, or k equals negative 3. All of the terms are 0, except over here at 3 omega naught we have 1/2, and at 5 omega naught we have k is equal to 1. Then here at our phase plot, everything is 0 except at k equals negative 5, where we have 90 degrees, and over here where we have k equals 5, we have negative 90 degrees. Example 2. For the following signal, find the magnitude and the phase spectrum. So this is very similar to the last problem. X of t is equal to 5 plus 3 e to the j 2 pi 1000t plus 30 degrees plus the cosine of 2 pi 3000t plus 2 times the sine of 2 pi 5000t. So these last two terms were in example 1, and we found that the fundamental frequency was 2 pi 1000 radians per second. So since that new term is at 2 pi 1000, our fundamental frequency is still omega naught is equal to 2 pi 1000 radians per second. So we can rewrite x of t in the following form. X of t is equal to 5e to the j0. So that would be a term at k equals 0. And plus 3e to the j 30 degrees times e to the j 2 pi 1000t. So this would be a term at k is equal to 1 plus, using Euler's identity, 1/2 e to the j 2 pi 3000t. That would be our term at k equals 3 plus 1/2 e to the negative j 2 pi 3000 t. And this would be our term at k equals -3 plus 1 e to the negative j 90 degrees e to the j 2 pi 5000 t. This is our term at k is equal to 5. And our last one is 1 e to the j 90 degrees e to the negative j 2 pi 5000 t. And this is our term at k equals -5. So once again, x of 0 is 5. X of 1 is 3 e to the j 30 degrees. X of 3 is 1/2. X of -3 is 1/2. X of 5 is 1 e to the negative j 90 degrees. And x of -5 is 1 e to the j 90 degrees. So using this, we can now plot our magnitude and our phase spectrum. So the magnitude of x of k we have here at 0, it's 5. At 1, we have 3. 2 is 0. 3 is 1/2. 4 is 0. And at 5, we have 1. So this is not completely symmetric because we only have the 3 at k equals 1. At k equals -1, we have 0. At k equals -2, we have 0. At k equals -3, we have 1/2. At k equals -4, we have 0. And at k equals -5, we have 1. So now let's create the phase spectrum. So once again, here's our axes, and the horizontal axis is k. The vertical axis is the angle for x of k, and it'll be in degrees. So at 0, the angle is 0. At 1, the angle is 30 degrees. At 2 and 3 and 4, the angle is 0. And at 5, the angle is -90 degrees. And on the other side, at -1, 2, 3, and 4, the angle is 0. And at -5, the angle is +90 degrees. And this concludes example 2. Example 3. For an impulse train with a period of t0, what are the Fourier series coefficients in Fourier series? You will also examine this phenomenon in lab. So here we have our periodic signal with a period of t0. So x of k is equal to 1 over t0, the integral over 1 period t0, x of t, e to the negative jk omega naught t dt. So this is equal to 1 over t0, the integral from -t0 over 2 to t0 over 2. The first thing I have to emphasize is you cannot integrate from 0 to t0 because the impulse is undefined at 0 and t0. You have to integrate over an impulse, not in the middle of an impulse. So when you integrate from -t0 to t0, you get delta of t, e to the negative jk omega naught t dt. Since we know the integral of an impulse is the area under the impulse is a 1, this becomes 1 over t0, because once again, using the sifting property, you're not only integrating over the area of the impulse, but you're evaluating this exponential at t equals 0, which is a 1 as well. So our Fourier series is 1 over t0. This is your magnitude, and the phase would be 0. So when you plot the magnitude spectrum, it looks like the following. You would have x of k, and here's k on your axis, and it actually looks like a unit impulse train where the amplitude of each of these is 1 over t0. And this is at the values of either k or omega. So in terms of k, I'd have 0, 1, 2, 3, dot, 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 or 0, -1, -2, -3, dot, dot, dot. Or in terms of omega, it'd just be 0, omega naught, 2 omega naught, 3 omega naught. Or in the negative axis, negative omega naught, -2 omega naught, -3 omega naught. In terms of the Fourier series approximation, this would be x of t is equal to the summation from k is equal to -infinity to infinity, 1 over t naught e to the jk omega naught t, or 1 over t naught, the summation from k equals -infinity to infinity, e to the jk omega naught t, which equals to the summation from k equals -infinity to infinity of delta of t minus kt naught, which was our original plot. So solving this for the summation, we have that the summation from k equals -infinity to infinity, e to the jk omega naught t is equal to t naught times the summation from k equals -infinity to infinity of delta of t minus k t naught. And this concludes example 3. Example 4. For the following signal x of t, what is the Fourier series and spectrum plots? Notice here that we have x of t is a ramp train. So the first thing you should notice here is that the fundamental period t naught is equal to 1 second. So omega naught, the fundamental frequency, is equal to 2 pi radians per second. And x of k is equal to 1 over t naught, the integral over 1 period, t naught, x of t, e to the negative jk omega naught t dt. And for 1 period, the equation of this line here is 4t minus 2. So I can write my integral as 1 times the integral from 0 to 1, 4t minus 2, e to the negative j 2 pi kt dt. If k is equal to 0, we can find x of 0. So if k is equal to 0, x of 0 is equal to the integral from 0 to 1, 4t minus 2 dt, which equals 4t squared over 2 minus 2t evaluated from 0 to 1, which equals 0. So x of 0 is equal to 0. So what if k is not equal to 0? X of k is equal to 4 times the integral from 0 to 1 t e to the negative j 2 pi kt dt minus 2 times the integral from 0 to 1 e to the negative j 2 pi kt dt. So for this first integral, we're going to have to use integration by parts. So if we let u equals t, du equals dt, dv equals e to the negative j 2 pi kt dt, then v is equal to 1 over negative j 2 pi k e to the negative j 2 pi kt. Remember, for integration by parts, when we make these substitutions, we write uv minus the integral of v du. So now x of k becomes 4 times the quantity t over negative j 2 pi k e to the negative j 2 pi kt evaluated from 0 to 1 minus 1 over negative j 2 pi k, the integral from 0 to 1 e to the negative j 2 pi kt dt minus 2 times the integral from 0 to 1 e to the negative j 2 pi kt dt. So now we're going to skip some of the steps, but by simplifying this, you get that the final answer is negative 2 over j pi k, or 2j over pi k. I encourage the viewer to go through and complete all of these steps to see how we arrive at this final answer. So in summary, x of k is equal to 0 when k is equal to 0, and it's equal to 2j over pi k when k is not equal to 0. And we have x of t, the Fourier series, is equal to the summation, if it's approximation, from negative n to negative 1, 2j over pi k, e to the j, 2 pi kt, plus the summation from k equals 1 to n, 2j over pi k, e to the j, 2 pi kt. Notice, very important that you cannot write the summation from negative n to n, because then you would get that middle term, which would be divide by 0. So you have to separate it into these two summations so that you catch the fact that x of 0 is 0. So here we have a plot of the pulse train with a period of 1 second. And now let's take a look at the magnitude and the phase spectrum. So here we have the magnitude and the phase spectrum for two harmonics. The first thing you should notice for the magnitude is that x of 0 is indeed 0. And then at x of 1, we have 2 over pi, which is about 0.67 or so. And then for x equals 2, we have 2 over 2 pi, which is somewhere close to 0.3. For 2j over pi k, we have the phase spectrum, where if k is positive, the angles are 90 degrees, and if k is negative, the angles are negative 90 degrees. And here we have the Fourier series approximation for the ramp train, where we have n equals 5, where it's starting to track a little bit, but there's only 5 sinusoids, n equals 25 and n equals 50, where the original signal is the dash line, and you can see that by the time we get to n equals 50, the Fourier series approximation is pretty good, except at those discontinuous points, which are that Gibbs phenomenon that we discussed before. Finally, some useful properties of Fourier series are that for x of t even and real valued, x of k is also even and real valued, or displays Hermitian symmetry. For x of t odd and real valued, x of k is even and purely imaginary, and also still demonstrates Hermitian symmetry. Some of the other properties are linearity, periodicity, time shifting, frequency shifting, conjugation, time reversal, time integration, multiplication, convolution, change of period, and time scaling. And this concludes lecture 3-2 on Fourier series.